To talk about another rule, and of course a symbol notation, but I will try to start teaching and continue writing everything myself because I have to immediately leave home to school. There is another group coming there, and I have to be there at 11. So let me just start doing them, and after I am finalized my lesson, you can work on yourself, and then I can actually go to school. So there is another rule. It's called the complement rule in combinatorics, and of course this is something so trivial again that already you know about that, but let me just mention it here again because it is sometimes useful to think in this way. And then of course then I will introduce a new notation or symbol called factorial of an integer, of a non-negative integer for you. Okay, so what is the complement rule? So the complement rule is very simple. The number of desired possibilities is equal to the total number of possibilities minus the number of undesired possibilities. It is completely clear, yes? But you might think that how this become helpful, but you can immediately see this in this problem, in this very simple example. Sometimes thinking in this complement way is easier for us, okay? So I want to motivate you that somehow this is sometimes a good strategy to tackle the counting problem at hand. So for example, consider the following problem. I have written it in blue, okay? Using only 0, 1, 2, 3, and 4 as digits, how many 3-digit numbers with distinct digits can be written? Of course, so it's very easy for you right now. You even don't need the complement rule. But I have solved this problem into two different ways. Using the product rule, using the product and complement rules, okay? So if I want to solve the first one, number 1, if I want to use the product rule, I would say that okay, I want to write a 3-digit number, so I have a task with 3 stages, yes, stage 1, stage 2, and stage 3. Of course, I wrote it in this order. This natural order is the best one because you know that there is some restriction for the left hand digit. It cannot be equal to 0. So let me call it stage 1, stage 2, and a stage 3. Okay, in how many ways I can accomplish the stage 1? I can put any number that I like there except 0. So there are 4 possibilities here, 1, 2, 3, and 4, yes? But then I am not allowed to repeat any digit, and I want to know how many ways I can do stage number 2, okay? This time, so the first, I will cross one of these numbers away, but in the second stage, 0 can also be chosen, so again I will have 4, and then finally S3 I will have 3. Of course this is very simple, and then you know you multiply these because they are independent actually, so it becomes 48. It was so simple that I myself prefer to solve this problem using this method. But to understand the idea behind the complement rule, let me also solve this problem using the complement rule. Okay? So the complement rule, somehow I would say that okay, I will start counting all possible codes, not numbers. I want to start to counting all possible codes so that I can write with these digits without repetition. Then this is the total number of possibilities if I consider all the codes. But I know there are some desired parts and undesired parts, yes? The desired parts are those who don't start with 0. The undesired parts are the one that start with 0. So then I subtract this from the total number of possibilities. What you would expect to get 48 back again. Yes. So what we do, if I want to do number 2, I would say that, okay, the total number of codes, let me for example write the total number of codes without repetition of digits. Okay, so how can I calculate this? Again, I have a 3-stage task, but I don't have any limitations here except that I'm not allowed to repeat any digit. So I would write stage 1, stage 2, and a stage 3. And then what I do, stage number 1 can be filled up with 5 possibilities, yes, because I am just counting the codes. But then the next one would be 4 because I'm not allowed to repeat what I put in the first one, and then the next one would be 3. So if I multiply this, it becomes 60. So there are 60 possibilities in total, okay? But all of them are not the desired ones, because I know when I count in this way, I'm also counting some of the numbers which start with 0, but I don't want them here. So I would say I want to calculate the number of undesired ones, yes? So this is the total possibility. Total number of possibilities. Yes, and then I would say the codes that start with 0. Okay, so if it seems that I am doing a completely different problem. I want to count the number of codes that start with 0. Okay, so again, I have a 3-stage task, but a stage 1, what should I put for a stage 1? I am counting the number of codes starting with 0. So there is only one possibility here. I want to put 0 there. There is only one possibility. Okay, but now 0 is gone, and I go to stage 2. In stage 2, how many of them are available is 4. And in stage 3, because repetition is not allowed, I have only 3 options left. And if I multiply them, it becomes 12. Total, this is the undesired, the number of undesired items. So therefore the question mark that I am looking for is 60 minus 12, and this is exactly the same number, 48 again. Of course, in this problem, using the complement rule is not making the problem easier, it's making the problem harder. But sometimes thinking about the complement rule can indeed make the problem makes the problem easier. So for example, let us consider example 2. Okay, how many 3-digit numbers are there so that each contains at least 1 5? Okay. Here, what do you think? Do you think using the complement rule is better, or just the direct using? Because first of all, this is not possible, as I understand, using exactly one product rule, yes, to calculate this here. So it means that I need to consider different scenarios, because when you say there is at least 1 5, it means that this 5 can be the left digit, it can be the middle digit, it can be the right hand digit. So it might have 2, it might have 2 5s, it might have 3 5s. We need to consider all these scenarios. Of course, if we start counting all of these possibilities and then add them together, then of course it becomes the answer, and that's correct. But you see that you need to consider different cases. Okay, so this is very important to understand. How can we recognize a complement, the complement of what we are counting? So I think this is a good idea to have a Venn diagram again. So here the parts, the sizes of the parts are not into scale. So assume that this is the total possibilities. This is the total 3-digit numbers that I can write. Okay? If I look at these numbers, there are some possibilities going on with respect to 5. Some of them does not have any 5s. Yes, so I can consider them without 5. So let me write here like this: number of 5s is equal to 0. Number of 5s is equal to 1. And then we have another one: number of 5s is equal to 2, and number of 5s is equal to 3. Yes. Okay, which are the parts that we are, what are the desired parts? 3-digit numbers, so that each contains at least 1 5. So it means that this part is the desired part, because in this part we have 1 5, in this part we have 2 5s, in this part we have 3 5s. Yes, and we want to have at least 1 5. So you see, if I want to start counting this directly, I have to use the product rule for each part, and then use the sum rule for adding these numbers. And by the way, you know that the sum rule is applicable because there is no intersection between these parts. If a number has exactly 1 5, it cannot simultaneously simultaneously have 2 5s, and etc. So none of these numbers are actually, there is no single number that is in both of them, in more than one of these parts. Okay, so if you want to use the old method, you need to calculate each one, the number of items in each one of these 3, and add them. But you see, the complement one is only one part. Okay, so this is easier, I would say, if we concentrate and calculating the number of elements here and calculate the total number of elements here and then subtract them. Okay, so I don't know, this is one way, of course, but I would say it's very instructive if you want to learn combinatorics. It's always very good to confirm this calculation using the direct method, counting these and then adding them together. Okay, so let us see how this goes. So I would say that this is the total. Yes, this is total, and this is the desired one. No, undesired one, and this is the desired part. Okay, so let us concentrate on calculating the total number first. So the total number is probably easy. We want to calculate all 3-digit numbers. Yes. So number of total items is how much? Is of course 900. Yes, there are 900 3-digit numbers. You can also use the product rule to calculate this 9, 10, 10. Yes, but it is very clear. And then undesired one, it means that I want to count the number of 3-digit numbers without any digit 5. Okay, so for calculating this undesired part, so what can I do? I am facing a 3-stage task. But be careful here. The only restriction here is that I am not allowed to use 5. Okay, so here how many digits are possible? So let me write the stage 1, stage 2, stage 3. For stage 1, of course, I know that there is no 0 that I can put, and because of this undesired part, I'm not allowed to put 5, so I will have only 8 options available. In the next one, what happens is that I can put 0, but still I am not allowed to put the 5. So this becomes 9. And then the other one is also 9. Yes? And then if I multiply, so this becomes 8 times 81, so which is this one. So the question mark that I am looking for is 900 minus 648. So it becomes 252. Yes, am I right? Let me double check these calculations using my calculator today. I'm a little bit tired. So 8 times 9 times 9. Yes, that's correct. And minus 900. That's also correct. Is that understandable for everyone?
Yes.
Yeah. So, but by the way, I don't know. I think that's a good exercise if you try to count it in the. So, for example, this one is easy. There are 3 5s. Okay, so that the only option is 555. Okay, but here I have 2 5s. So here this is not, again, because if you have 2 5s, you can have 2 5s in these positions, you can have 2 5s in these positions, and then you can have these 5s in these positions. So you need to consider all of them. So you need to more or less separate these possibilities for these cases. And when it comes to one number of 5, again, you can have 5 here, you can have 5 here, you can have 5 here. So I would say that it is possible, but I hope that you agree with me that solving the problem in this way is easier this time, using the complement rule, even though in the first example the product rule was easier. Okay, if you don't have any questions, let us go to number 3. How many 3-digit numbers are there so that each contains a digit? I would say that you can see the problem here. Let me give you a little bit of time so that you can work on it yourself, okay? Did you come up with any answers? Of course, one of them here is the complement one. The second one, I couldn't think about using the complement method. Did you get any answer for the first part? The first part, I would say it's easy. That's exactly complement rule. No answers?
I got 836.
Yes, 836. Yes, that's correct. That's actually, I would say that's the number that I got. Okay, so here we want to have each contain a digit less than 6. So what I would say, so let me write the numbers here. So the digits that I can use is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The total number, of course, I know what is the total number of 3-digit numbers is 900. My desired items are those who contain at least 1 digit less than 6. It means that it should contain at least one of these digits. Okay? So let me count the number of items that are only constructed using these items. Okay? If I take this away, then what is left for me is the number of items that uses at least one of these digits, yes? But that is, I don't know, is that understandable for everyone? Okay, so I am counting the total number of items that are only constructed using these numbers. Okay, if you take these numbers away, that I am constructing only with these numbers, then what is left for me contains at least one of these elements, yes? Okay, so how many items I can, so undesired ones, number of undesired ones is equal to, I have a 3-stage task, but I am using only these last 4 digits. So the first one is 4. Stage 1 can be done in 4 different ways because nothing is mentioned about the repetition. It means repetition is allowed. So this means that all of them is 4, and if I calculate, it becomes 64. So this means that the question mark here becomes equal to 900 minus 64, which, as you said, is 836. Is that understandable for everyone? And again, you see that this is a very, very nice trick, because if you want to count them directly, then you need to consider a lot of possibilities. Okay, so, but for the next one, I thought that it might be interesting if we also solve this one. It doesn't mean that this depends on the complement rule. At least the way that I was thinking is not coming from the complement rule. So, how many of them contain exactly 1 digit less than 6? Okay, so exactly 1 digit less than 6, it means that it should contain exactly one of them, but of course you see that 0 is also a little bit problematic here. Yes, so this might motivate you to consider these two scenarios differently. So I would say that, okay, let me have this, something like Venn diagram for myself. So I would say that having 0, so having 0 as the digit less than 6, as the digit less than 6, okay, or having these numbers 1, 2, 3, 4, 5 as the digit, not having all of them, or actually it should be written or, yes, so you know this means or, as the digits less than 6. So I am interested in both of them. So I will count the number of elements here, the number of elements here, and then add them. The reason that I can use addition rule is because there is no item in common between these two parts. Yes? Okay, if I want to do this, I don't know how did you calculated that. So I know that I have to choose 0, and I need to put it somewhere in 3 positions, either in the in 2 positions, either in the middle digit or on the right hand digit. Okay, so I would say that I have I can write it in 4 stages, choosing, yeah, so let me write it in this way. So it becomes a little bit complicated if I want to say in this way. So what I do, I would say that there, how many options are there available for putting 0 in my 3-digit number? I cannot put 0 in the left hand side, but I can put it as the middle one and the right one. So I have a 2 because I can do this task in 2 different ways. So you see, I have my 0 in my hand now because I have to choose 0. But then I want to put this 0 somewhere appropriate in a 3-digit number. I cannot put it on the left, so there are 2 options available that I can put them there. Either, so if I have this number and that number and that number, so I cannot put 0 here. Either I choose put 0 here, or I can choose put 0 here, and it doesn't matter. Assume that you chose here and put 0 there. Okay? But then you need to start choosing a number from these digits, because no longer you are allowed to choose any number of this, because you are supposed to have exactly 1 digit less than 6. So it means that from these you have to choose four. There is 4 possibility for putting something here. There is also 4 possibility to put something here. So if you multiply all these numbers, it becomes 32. So is that understandable? Okay, so what I'm saying is that one task is to choose the position for the 0. This task can be done in 2 different ways. Either I can put it here or there. Now assume that the first task is accomplished in one of these ways. For example, assume that you put 0 here. Then there are 2 other digits that you need to fill in. But you are not allowed to choose these digits from these numbers because you want to have exactly 1 digit less than 6. So it means that you have 4 options available for filling up this number and 4 options available for filling up this number. So in general, you have 32 options if you want to have that digit to be 0. But now let us go to the next one. This time I want to choose one of them. So I don't have any problem. 0 is not in my number. So first of all, I have 5 options, but I have to choose one of them. So this time I have 5 options available to choose one of these numbers. One of these numbers is chosen now, and I have to put that number somewhere in these 3. So how many options are available for me? I have 3 options. Yes. Either I can put it here or here or here. But now assume that I have decided and put it here. Then there are 2 more options for me, 2 digits for me, so that I have to fill them through these numbers. So again, this becomes 4 and 4. So this becomes 5 times 3 times 4 times 4. And then it becomes 240. And now the items that I want to count is 240 plus 32, which is 272. Yes, is that understandable? So let me just explain here. So here I have 0. 0 is in my hand. I want to have 0 in my 3-digit number. I have 2 options, 2 positions available for 0. So the first task is to put 0 somewhere, can be accomplished in 2 ways. Assume that in one way this is done. For example, assume that you put 0 here. Then you have to fill up these numbers, these digits, with one of these options available. So there are 32 of them containing 0 as the only digit less than 6. Now we want to have another option. Here, of course, you can count them one by one, but it is useless to do this because it takes time. You can consider 1 separately, 2 separately, 3 separately, but there is no reason to separate these items anymore. What I do, I would say that, okay, now I want to choose one of these numbers. I have 5 options available. Now that I have this number chosen and it is in my hand, I have to put it somewhere in my 3-digit number. But I do not have any restrictions here, so there are 3 more options available for me to put that number, this is in my hand now, put it in its place. For example, assume that I did it here, then again I have 4 and 4. So multiplying 5 by 3 by 4 by 4, it gives me 240. And then if I want to answer the question, I have to add these 2 numbers. Okay, hopefully there is no mistake. There is no problems here. Okay, now let us start. This is also in the book, the Factorial. I want to define this symbol. If you have, I don't know, if you have seen some of in the combinatorial problems, there are many cases that we have to multiply consecutive integers together. So, and then instead of working with big products, we invent actually a piece of notation so that we can summarize and write those products compactly, more compactly. So let n be a non-negative integer. So it can be 0, 1, 2, 3, 4, etc., etc. the factorial of n is denoted by this symbol. You put an exclamation mark in front of it, and it is defined as follows. If I give you 0 for n, you answer 1. This is the definition. If I give you 1, you again answer 1. But if I give you any number greater than or equal to 2, you start from that number that I give you, and you start multiplying that number by the previous number, by the previous number. You continue this way until you reach to the first integer, to the first natural number 1. Okay? So for example, if I want to solve this example, 1 factorial just by definition is equal to 1. If I ask you what is 2 factorial, 2 factorial, you start from 2 and multiply it by the previous number, which is 1, and when you reach to 1, you will stop and do this product, which is 2. So 2 factorial is 2, and 3 factorial means I start with 3, multiplied by the previous number, multiplied by the previous number. When I reach to 1, I stop, I do the calculation, it becomes 6. So 3 factorial is 6. 4 factorial, I start from 4, multiplied by 3, multiplied by 2, multiplied by 1. Of course, I don't need to do this from scratch because you immediately understand this part itself is 3 factorial, which is already calculated. So what I need to do, I multiply 4 by 6, it becomes 24. And of course, you can also multiply 4 by 3 by 2 by 1, it becomes 24. And then you remember that factorial is also growing very, very fast. Okay, so 5 factorial is 5 times 3, 5 times 4 times 3 times 2 times 1. And if you do this product, it becomes 120. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. And finally, as wanted in the problem, this is 7 times 6 times 5 times 4 times 3 times 2 times 1, which becomes 5040. Okay, so this is just a piece of notation. Instead of writing the product so long, I can just write it compactly and say it's 7 factorial. Okay? So one important property I have written in this remark, I want you to know about that. So any factorial can be written as n multiplied by the previous factorial. And it depends how many times you want to use this. For example, I can write 30 factorials to be 30 multiplied by the previous factorial. Or if I want to, I can write it as the product of 30 times 29. If I decide to stop here, then I have to multiply by the 28 factorial. And then I can, of course, do it 30 times 29 times 28 and then 27 factorial. So this is very, very important to remember. Factorial of any number is equal to that number multiplied by the factorial of the previous number. So this is very important to remember. Okay, so that's also very, very simple exercise. I intentionally wrote it here because I wanted to get used to this. So if I want to calculate 5 factorial plus 2 factorials, it becomes, instead of 5 factorial, I have to write 5 times 4 times 3 times 2 times 1. Let me put a pair of brackets even though it is not needed. And instead of 2 factorial, I would write 2 times 1. So if I calculate the first product, as you saw in the previous page, it is 120 and that is 2. So the answer to this is 122. Okay? And then, I don't know, somehow I thought that some students might make mistakes. If I ask you to calculate this, you are not allowed to write, so for example, n plus m factorial is not equal to n factorial plus m factorial. That is wrong. Even n times m factorial is not equal to n factorial times n factorial. That is also wrong. Okay, so if you see something like this and you have to calculate, it means that the pair of brackets is prioritizing this addition inside the pair of brackets, so it becomes 7 factorial. And 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. And as we saw in the previous page, this is 5040. 40, and you see immediately these numbers are quite different. So especially these kind of fractions you should be able to simplify. So if I want to simplify that, what I do, I will, for example, I would say 12 factorial divided by 9 factorial. So in principle, I can write all the digits, all the factors in 12 factorial and all the factors in 9 factorial. But there is no need for that. I can use this remark. Yes, I can use this remark now. So instead of 12 factorial, I can write 12 multiplied by the previous number 11 multiplied by the previous number 10 multiplied by the previous number factorial. And that is clear. It's good to stop there, yes? And then divided by 9 factorial, because whatever 9 factorial is, it is common in the numerator and the denominator, so these two numbers can be simplified. And what is left for me is just simply 12 times 11 times 10, which is 1320. Okay, but this is my goal. My goal is to write it up to some point so that you can simplify these expressions without having to write all these elements, all these factors. So finally, number 4 in this example, what we can do is this. We have 13 factorials, and then I have 10 factorials multiplied. If there is nothing between them, it means that I am multiplying these factorials. Okay, so then the trick is again clear, hopefully, for everyone. Instead of 13 factorial, I can write 13 times 12 times 11 times 10 factorial. It's better to stop here, because now I have a 10 factorial in the denominator, so that can be simplified with that. But because there is nothing to simplify by 3 factorial, I have to write it down. So 3 times 2 times 1. So then what happens? This 10 factorial and that 10 factorial are gone, and then you know that this is 6, and 6 and 12 can be simplified. So that is also, that is also a 2. Yes, and if you multiply them, it becomes 286, I would suppose, yes. So 11 times this is 143. Yes, that's correct. So you see, these kind of simplifications you need to know when dealing with factorials. Another exercise, which is of course very simple, write this product as the quotient of 2 factorials. That's also important for us to know. So you see, if it was from 10, 9, 8, 7, and if it was just up to 1, of course I could write it 10 factorial. Even though this is a product of consecutive integers, but the problem is that it doesn't continue until 1. So I cannot just write it 10 factorial, but I can always write it as the quotient of 2 factorials. So what we do in principle, of course you don't need to write the details, but let me just do it. What I do, I would say that this expression is equal to 10 times 9 times 8 times 7 times 6 factorial, and then I cannot just multiply 6 factorial there unless I compensate for that by dividing it by another 6 factorial. So what I have done, I have rescaled this expression by 6 factorial. So the denominator, I keep it as it is because I am supposed to write it as the quotient of 2 factorials, and in the numerator, hopefully everyone agrees that 6 factorial means the product of 1 up to and including 6, and then I am continuing up to 10, so it means that the numerator is nothing except 10 factorial. So you see, be careful. When you have 10 factorial and 6 factorial, you are not able to simplify these things by 2 and saying 5 factorial, 3 factorial. Don't make these mistakes, please. This is the only thing that you can write, and you have stopped there. Okay, so number 7. Let us solve some problems here together that is a little bit more interesting. So let n be greater than 1 be an integer. Show that this is actually correct. So what we can do, I would start, this is an identity I want to show. So let us start with the right hand side, from the right hand side, because it's more involved, yes? So I would say right hand side is equal to. So let us see what we can do. This is one number, so let me multiply it here and there, yes? So this becomes n minus 1 multiplied by n minus 1 factorial, and then plus n minus 1 multiplied by n minus 2 factorials. Okay, if you understand what's going on, you can write it a little bit more compactly. Can you tell me how? What I'm saying is that, yes, exactly, thank you very much. Because you see, I told you that if you have n factorial, you can write it as that number multiplied by the previous number factorial. So this is two-sided. If you want to, you can decompose 1 factorial into the product like this on the right hand side. Or if a product of this type is given to you, and if you want to, you can collect it back into one single factorial. But what is important to realize is that these two numbers should differ exactly by 1, and this number should be smaller than that number. If that is the case, the answer becomes the bigger number factorial. And you see, this is exactly happening here. So yes, I have these two numbers are differing by 1 unit, and this one is smaller than this one. So this means that I can collect the second one. So I cannot do anything for the first one. You see, it is n minus 1 multiplied by n minus 1 factorial. But the next one can be collected as n minus 1 factorial. Yes? And now you see that n minus 1 factorial appears as a factor here and there, so I can factor it out. So this becomes n minus 1 plus 1 multiplied by n minus 1 factorial. So what I have done, I have pulled this out. So from this term, only this one is left, and when I pull this one out, so there is a 1 left there. But there is a better name for what is inside the pair of brackets, because 1 and minus 1 are gone, and it is just n. And then it is multiplied by n minus 1 factorial, and then you can immediately see that this is also n factorial. Yes? And that is exactly equal to the left-hand side. Okay. This is one exercise here. Another exercise using mathematical induction or otherwise. This otherwise is useful for the people who actually have mathematics specialization. I talked about telescopic sum, if you remember. So one trick to find this formula for this without having the right hand side is using the telescopic sum. Okay, might be we can solve that problem in math specialization. But here for Math 5, my intention was to use mathematical induction to prove this is right. Okay, so do you remember what we were supposed to do for mathematical induction? We check P of 1. So what is P of 1? On the left hand side, I have 1 times 1 factorial. On the right hand side, I will have 1 plus 1 factorial minus 1. I need to check the truth of this equality. Okay, but this is easy. The left hand side becomes what? 1 times 1 factorial, but 1 factorial based on definition is 1, so it becomes 1. The right hand side is 1 plus 1 factorial minus 1. But 1 plus 1 in pair brackets means 2 factorials minus 1. 2 factorials means 2 times 1 minus 1. Again, this becomes 2. So this, the left hand side is equal to the right hand side. So it means that P of 1 is true. Now we assume that this is true for K. So P of K. So what is P of K? Do you remember? I replace N with K everywhere. So assumed to be true, do you remember? Now P of K plus 1, this is something we have to show it is true based on this induction hypothesis, yes? So it means that now I have to replace K with K plus 1 everywhere. But if you remember your experience from the time we were working on mathematical induction, it is instructive when you write this K plus first step, it's better to copy the previous step as well. Okay, so we want to prove this is true. Okay, so this is an identity. I can start again from the left hand side, but from here to here, according to this one, is this expression, because this is assumed to be true. So I will replace this and put this expression in instead. So this becomes K plus 1 factorial minus 1. But then what you see afterward is this one single term. I have to add that one there. Okay? So still this expression is not exactly this expression. I have to work on it. This minus 1 is exactly here, so probably I don't need to do anything with that. But it becomes clear that between these two terms I can factor K plus 1 factorial out, yes? So this becomes K plus 1 factorial out. So from here only 1 is left because I pulled it out, and from here K plus 1 is left because I pulled this term out. So this becomes plus K plus 1. And then of course I have a negative 1 at the end, so that I have to write it down. Okay, so it's negative 1. But now you see that K plus 1 becomes K plus 2. So this becomes K plus 2 multiplied by K plus 1 factorial minus 1. And then what I can do, I can collect this thing. I hope that this combination is now easy for you to detect. Yes, I have a number multiplied by the previous number factorial. Previous number means 1 unit less than this. Okay, so this combination is nothing except K plus 2 factorials. And then I have a minus 1, and that's exactly what I'm supposed to show. So I used mathematical induction to prove this equality involving factorial notation. Any questions? Okay, there are 2 more examples, I would say. Yes, am I right? Yes. And then the lesson is finished. So determine n if n is a natural number such that n factorial is this expression. Okay, so I don't think that's a hard thing to do. We want to find a suitable value for n so that when we calculate n factorial, it becomes like this. Of course, if you see, that is the factorization of a number into prime factors. Okay? So, do you have any idea what to do? Because you know that on the left hand side you have a product of consecutive integers is starting from 1, 2, 3 up to some point n which we don't know, and we want to detect that point. Yes? Yes, exactly. We split the right hand side so that to see how many integer factors I can continue, and then all the factors are being used. Yes. So let me say, for example, I would say 2 to the power of 8 times 3 to power 4 times 5 to power 2 times 7. I can write it as 1 times because 1 doesn't have any role here. And then instead of 2, okay, I have a factor of 2. I want to write the product of consecutive natural numbers starting from 1, and to see that how many factors are available for me so that I can continue. Okay, so remember, I put 1, I'm not using any one of them, but when I write a 2 here, I am using one of these 2's. So I don't know which one is suitable. So from now on, I have only 7 2's available. And then I go to the next one is 3. So it means that I used one of my 3's. There are 3 3's left. And when I go to 4, 4 means I am consuming 2 factors of 2 because 4 is 2 to power 2. So it means that I no longer have 7 of them. I have now only 5 of them. And then when I go to number 5, I am using 1 factor of 5. So there is only 1 factor is left. And when I go to 6, I am consuming the 2 and 3 simultaneously. So it means that now there are 2 3's and there is only 4 2's left for me. And then I go to 7. Okay, 7 is the last factor, so there is no 7 left. And when I go to 8, 8 is 2 to power 3. Yes, so again 3 of them are used, so only 1 2 is left so far. And then when I go to 9, I am using 2 3's, so the 3's are also gone, finished. So, but still there are some factors left, and that is clear. When I go to 10, I am using the final 5 which was left for me. Do you see there was only 1 left, and there was only 1 2 left, and now nothing is actually left. Yes, nothing is left. So it means that, but on the other hand, this, if I ask you what is this product, you can immediately answer this is 10 factorial. So it means that when you say n factorial is 10 factorial, I can conclude that n, my natural number n, is actually 10. Yeah, I think that is also one way to look at this problem. Might be the most interesting problem is this one. I have defined S for you as 1 factorial plus 2 factorial plus 3 factorials up to 19 factorials. Of course, that is a huge number. And then I am asking determine the unit digit of S squared. So it means that I want to raise it to power 2. Of course, it becomes again another huge number. But what I want to determine immediately is the rightmost digit, the unit digit of S squared. This is good because I want you to know something. Do you have any idea what to do? The trick is this. Let me show you this list. Might be you can see something here. So these are small factorials. 1 factorial up to 6 factorial, 7 factorial. Something interesting happens, yes? So can you talk about the unit digit of factorials here? Do you see any pattern? The unit digit of factorials. Yes?
They are always except for 1.
Yes, so that is one thing. But we can be more specific than that.
The unit digit becomes 0 as n increases.
Yes. Why is that? You see, of course, up to here, it is not 0, but it is guaranteed that the unit digit remains 0 until forever, yes? Why is that? Because 5 factorial happened to be 120, so the unit digit is 0.
Because 5 plus 2 is always 5 times
Exactly, exactly. So for example, what is 6 factorial? 6 factorial is the previous factorial multiplied by 6. The previous factorial ends with a 0. So if I multiply it by 6, whatever the number become, what happens is that the unit digit is again 0. Now that 6 factorial ends with 0, I want to calculate 7 factorial, but 7 factorial is 7 on the previous one. And as of course Alex also told, that's also a good way to see that. Because if we go beyond 4 factorial, we definitely will have a factor of 2 and a factor of 5 in our factorial. So then this means a factor of 10, so it means that the unit digit of all these starting from 5 factorial onwards is actually 0. So this is why this problem is not that hard that might look in the first sight. So here, if I want to answer this, I would say that S is a number like this. 1 factorial is of course 1. 2 factorial is 2. 3 factorial is 1 times 2 times 3 is 6. 4 factorial is 24. Let me write 5 factorial is 120. The other one is 720. And I don't know the 19 factorial, but 19 factorial is something that I don't know, but the last digit is 0. So S is, if I calculate this part, it's easy, it is 33. And then if I ask you what is this, I don't know exactly because I haven't calculated the numbers, but I know that all the unit digits that I have from here to here is 0. So this means that if I add these things, then it becomes a number which I don't know, but it ends with 0. Yes, that is clear. And now if I have a number which ends with 0 and I add 33 to it, then again I don't know what is happening here, but this will end with 3. Okay, so if you ask me what is this number, of course I don't know, but I can say about the unit digit of S, the unit digit of S is definitely a 3. You can use the calculator or computer to confirm that. And then if a number ends with a 3, S squared definitely ends with, so therefore S squared is again a number which I don't know, but it will end with 9. So the answer to this question is 9. The unit digit of this number squared is a 9. So that is also something might be interesting relating this factorial symbol that we learned today to the number theory that we have already learned before. Okay, any questions? Okay, so thank you. I will end this.